دكتور بنزلوا فايلين.
Okay, failing. Okay, welcome again. Now we're going to start talking about real-time operating systems. طيب. Real-time operating systems. Real-time operating systems are operating systems that work in real time. Usually, they call them RTOS or real-time kernels. Real-time kernel to manage, to work as an operating system for microcontrollers, for embedded systems, for systems that are resource constrained. You guys already dealt with operating systems, right? Anybody didn't ever deal with an operating system?
Deal how يعني.
معرفة عامة.
Use it. I'm not asking if you studied operating systems in your undergrad. I know if you're not a computer engineering undergrad, you didn't take operating systems. But you, as a user, did you use an operating system? Well, your machine right now, you're plugged into this class. You're using a machine, a phone, or a laptop, or whatever. You have an operating system running on the machine, right?
Yes.
You have Windows or Linux or Android or iOS. These are called operating systems, right? So we're going to talk about operating systems. Operating systems, undergrad and grad, and I took like 2 or 3 classes in my operating systems, advanced operating systems, distributed operating systems, okay? And it's a topic about how to make a piece of software, kernel, sometimes they call it, to manage your software running on a certain hardware, and to interact as the interface between the hardware and the software, and manage what task is time to run, what are the tasks are running concurrently, and so on. Operating systems. But what's special here, real-time operating systems, we're talking about operating systems that need to run on safety critical or real-time or computers that need to operate in real time, and not acceptable to have bugs or restarts or whatever, because these microcontrollers are usually controlling systems that need to run in real time. No acceptable delays, no acceptable malfunctions, whatever. So, and I'm gonna cover in this coming hour, maybe, the topic of what is a real-time operating system with a case study on an operating system called MicroCOS2, RTOS, that I'll show you how we get it and how we install it in our microcontroller, on our HCS12 microcontroller. Most of you are not CE background. Anybody studied an operating system class in the past? Most of you not?
For me, I'm not.
Okay. but CE people, CS people study operating system classes. It's a big topic. But I'm gonna concentrate on some very important things that will make us understand the basics of an operating system, and then reflect it on our case, that MicroCOS2 that we are going to use for this microcontroller. So I'll give you an introduction. We'll look at conventional foreground background systems. Then what is a real-time kernel or real-time operating system? What is being preemptive or non-preemptive in operating systems? Tasks, what are tasks and task states? Task control blocks, scheduling, what is a scheduler? What is context switching? These are basics of OS. Semaphores and mutual exclusions, deadlocks, and how tasks can talk to each other in inter-task communication, and how memory management is going to happen. So the operating system we're going to deal with here in this class is called micro CEOS2. Micro C comes from microcontroller operating system version 2. Recently, they have in 2019 they released version 3, but personally I didn't download it. I didn't deal with it, but it should be the same concept. And they write it, and the author or the creator of this operating system has authored a book called Micro CEOS2. I used to have it. Maybe you guys can get a copy of it. They write it micro, not micro, for archiving in the bookstores and libraries purposes. And they use the dash, so people read it micro CEOS2 split, not mucos. Okay, any micro CEOS2. This what makes this micro CEOS2 my choice to cover in this class. First, it is certified by the FAA, the Federal Aviation Administration in the United States, to be used in commercial aircrafts. Certified. So it is reliable. It is real time. It is also open source for research and academic purposes. Okay. You can get the source code of it, which is really great. So when you look inside an operating system and see how it works, it makes you understand how operating systems work. Right, to start with, without operating system, and all what we have developing using C code on our HCS12 controller here, we had a main loop, right? We had a main loop. We write task 1, read switch 1. If it is pressed, do this. If it's not, do this. Then read the potentiometer on the analog port 7, right? Convert the reading into a scale of 0 to 235, generate a PD. So task 1, 2, right? Everything, anything you do, reading the button is a task. Reading the potentiometer is a task. Turning on LED is a task. Generating a PWM signal is a task. Okay, these are all tasks. We used to write them in the same infinite loop, right? Task 1, task 2, task 3, task 4. Sometimes you can get interrupt service routines. Okay, so anything running in the main loop, they call it a background task. And you have foreground tasks, like the interrupt service routines that can pop up, stop a background task and take higher priority.
دكتور بيسموه بلوك صح هو الانتربت؟
الانتربت بلوك؟ I don't know يعني I don't know who يعني مين هم اللي بيسموه interrupt service routine. I don't know what a block what you mean by a block.
لأنه يعني أنا قرأت إنه البريوريتي بيكون للو بريوريتي، بعدين لما مثلا بالدول سبيد لما يصير بلوك هابند يصير انتربت، فبروح على الهاير بريوريتي بيعمل هاي سبيد.
Okay. ماشي. Thank you. Salah is talking, right?
Yes, دكتور.
Yeah, Salah. طيب. Interrupts are the way to do context switching and moving between tasks. I'll talk about that in the OS when we go to the OS. And how this may cause in preemptive systems, this may cause priority in inversion. Now, every task has a block, a task control block that contains all the information about the task. Where is its stack? What's its priority? The register values, whatever. But really, I'm not sure if I understand your question, but I hope I cover it while we're going. So foreground or background tasks, here is our infinite loop, right? Our main loop for ever, do something, then do another thing, then do a third thing. While you're running, you may get an interrupt service routine that interrupts you, and here do something. Then you go back. When you're done, return from interrupt, continue to task 2, maybe do nothing, delay, whatever. You may get another interrupt, and the interrupt gets interrupted. So you get a foreground, a second level foreground. When you're done, you go back. If this is hyper, you go back to the original interrupt service routine. And when you're done, you go to your original task and keep doing this forever. This is foreground background systems. This is the normal way that we use in simple embedded systems development, software development. Something in code that looks like this. Our main background loop forever. Do task 1, task 2, task 3, whatever. Asynchronous at any point of time. If an IRQ happens, the interrupt service routine for the IRQ will come and execute the code you have here. At any point of time, the RTI interrupt may happen and bring you to execute something here, I++, and then you go back where you were, and so on. So these are the foreground tasks that are mainly interrupt service routines that interrupt the normal execution in the background loop. That is usually sequential. Sequential. Okay. Advantages of this way of writing embedded code: it is low cost and used for low cost embedded applications because you don't need an operating system, pay money for it, pay license fees, whatever. Memory requirements depend on the application. You don't need specific memory requirements for the OS because this is overhead. You only have a single stack to control the pushing the registers and return addresses and whatever for the interrupt service routine, local variables and functions, right? So single stack area and minimal interrupt latency. You only have latency. When you have an interrupt, you go execute the interrupt. Before you go, you have some latency to push the return address and status of the CPU. You go execute and come back. This is the only latency. It is minimal. Low cost. You don't pay for anybody. Okay. These are advantages. You can look at them as advantages. Simple. And really, this is what you need in most of the embedded applications, and an embedded system controlling an AC, air condition. Yeah, you need to read the temperature sensor, check the set point from the user. If greater, turn on the compressor, not do the and so on. Very simple. It's not smart to make it more complex. You may run into more getting bugs or whatever. That's why in embedded systems, there is a law. When I was in the automotive industry, we were not allowed to use pointers. We're writing C, but we're not allowed to use pointers, because there is a probability to lose track, okay, and so on. Be simple. That's something important. But sometimes complexity gets higher and higher. You need something to help you. The disadvantages of foreground background systems is that the background response time task for the background response time is non-deterministic, because this task, مثلا, read the push button. If the push button is pressed, you do task 2. If it's not pressed, you go to task 4, مثلا, right? So the time where you're gonna reach task 4 depends on if this is gonna be executed or not, if the button is pressed or not, right? So you don't know exactly when task 4 is gonna get its time to run, because a lot of uncertainties here, right? Affected by if conditions, by for loops, by whatever, any decision making, right? So non-deterministic, you cannot guarantee 100% when a task is going to be executed. That's the first thing. Also affected by the asynchronous events, the foreground tasks. When you don't know when an interrupt is going to happen, and if an interrupt happens, this will push everything afterwards. If it doesn't happen, everything will happen before. Okay. May not be responsive enough, because you may get stuck in some task waiting, push button for, you may have 100 tasks before. At certain point of time, these are 100 if conditions. They may be all false and you get here real quick. They may be all true and take time to get here. Okay. And this timing thing changes as you change your code. Anytime you add a few lines of code here, this will affect the timing of everything afterwards. And even before, because it's a loop, it will affect the time of everything. This is a disadvantage. Okay. Another disadvantage is that all tasks have the same priority. And if you're here, the microcontroller will not understand that checking the push button that is checked in task 1 is higher priority, as while you're here, there is nothing going to move you to here, except that you will have to finish and go back in the loop. So they are all of same priority. Nothing more important than anything else. Reading a push button, turning on a compressor, reading a potentiometer, reading a serial channel, all the same priority. Okay. Another disadvantage in foreground background systems that we as software engineers, embedded software engineers, need to implement all services. مثلا, our time delays, timeouts, timers, message passing interfaces, managing the resources, managing who's going to use the to imagine that now you guys are working on a project, right? So you may be one controller could be used. This is the case. One controller is used to control the engine of a car, of a vehicle, engine controller. And hundreds of tasks will be running on that controller by hundreds of teams. طيب. Does everybody want to go write his own service functions, timers, مثلا? طيب. Bilal is working on something, Salah is working on something. I need the output from the thing that Salah is working on. How is he going to pass me that information? He is going to read the RPM sensors, compute the RPM of the wheel speeds of a car or a vehicle, and send it to me to use this RPM in another module to compute how, I don't know, the misfire control thing. How is he going to pass it? Through a global variable, a message passing interface, whatever. Okay, so when you're in big teams, you're not developing the whole system from scratch. If you're in a class project, you're doing everything yourself. You don't care about these things. But we're talking about embedded engineers, embedded software engineers working on big projects, teams working together, hundreds of people working together. There should be something that manages it. Maybe Salah is going to go use this the real-time interrupt for timers to generate time delays. Somebody else needs the real-time interrupt to do something periodic. Okay, what's going to manage it? We have one H bridge on our controller. You may want to use, okay, who's going to manage this resource? Who's going to manage memory space, certain shared memory space in memory? Who's going to use the parallel port? Okay, these are all low-level services that we need to care about as embedded engineers. Okay, and the code maintenance becomes harder and becomes more messy with time. So in big projects, I'm not saying go to real-time operating systems all the time, but in big projects, when you're always improving, working, adding features, things like that, an operating system will be a lot of help. Let's look at what an operating system can do, a real-time operating system or a real-time kernel. So a real-time kernel is a software that manages the time of a microprocessor or microcontroller. Manages time of the microcontroller. And ensures that most of the imported code run first. It has priorities. It also allows multitasking. Multitasking through time sharing. Yani today we have dual core and quad core and different cores in our computers to understand this. But in the old days when we had the Pentiums, we only had one CPU, right? One processor, one core. How were we able to run Word and run the calculator and run PowerPoint? All you see them all together and read the mouse and everything. They were using one processor, one CPU with one program counter, fetching one instruction at a time and running one instruction at a time. But how were we able to do multitasking? Time division. So you give 2 milliseconds for task 1, 2 milliseconds for task 2, 2 milliseconds for task 3, and so on. So in 2 milliseconds, I'm not going to do anything in 2 milliseconds, right? So you'll be able to read my mouse reading and display a frame on the screen and whatever, right? So through time sharing. So with a single processor, we will be able to do multitasking, running multiple tasks at the same time from the user perspective, not the CPU perspective. And here in our HCS12, when we do our demo, we only have one processor, one program counter, but we will do some demo with each other. We will do 2 or 3 tasks running at the same time. You will feel that they are running at the same time. So real-time kernels allow multitasking. They also provide a lot of services like time delays, semaphore management. I'll talk what are semaphores and mutual exclusions for resource management, and provide inter-task communication, tasks, methods or ways for tasks to talk to each other. And when we talk about kernels, kernels are either preemptive or non-preemptive. We'll see what is preemptive, what is non-preemptive, but preemptive, in general, preemptive kernels allow higher priority tasks to stop lower priority tasks and take the CPU over. But this has a problem of starvation. Starvation means a lower priority task. Every time a higher priority task comes, okay, it will stop. When it's time to run, maybe another higher priority task will come, it will stop, and the higher priority task will come. This can happen forever. So the lower priority task may not get the chance to get access to the CPU and never execute. So it may starve to death, starvation. It has a problem. It has a solution, sorry, called aging. You may raise the priority of a task with time. So now its priority is at level 10. Then I bring it up to level 9 after 10 cycles. After another 10 cycles, I bring it up to 8 until at the end it will become aging, right? It gets older, it gets more priority. And there are non-preemptive kernels where all tasks are the same. No task is more important than another. So whenever, well, you may have some priority, but while a task is running, even if it's lower priority, a higher priority task will need to wait for it to finish. Will need to wait for it to finish to get the CPU. But if 2 tasks come, the higher priority one will get the CPU first. But once the lower one gets access to the CPU, nobody can take it from it. It has to finish. Non-preemptive. So here's an example of non-preemptive kernels. You have a lower priority task running here. An interrupt service routine comes over. So imagine this interrupt service routine, ya shabab. Imagine it just like a periodic interrupt we write. Yani at the end, if I want to ask you, how would you, if you're asked to do a project for this class to build your own real-time kernel, allow multiple tasks to run at the same time, you may want to think of a periodic interrupt through using the real-time interrupt or whatever that happens every 1 millisecond, 2 milliseconds, and checks a set of tasks and says, now it's your turn, run task 1, then run task 2, run task 3. So we have an interrupt service routine that should come up periodically to check whose turn is it now. Okay, so an interrupt service routine interrupts the task, checks for other tasks. If there are other higher priority tasks ready, run them. Okay. If they're not, don't run them. So non-preemptive here, an interrupt service routine discovered a higher priority task, but it did not give it the CPU. It went back to the lower priority task until it finished. Then next, when it's done, the higher priority task will start running. Okay, so the interrupt service routine here discovered that there is a new task that needs to run, but it didn't run it immediately here. Okay, it waited for the lower priority task to finish, then it went to the higher priority task. This is called non-preemptive. We did not allow this higher priority task to interrupt or take over the CPU from the lower priority task. In preemptive, no, it will allow. So you have a lower priority task running. Interrupt discovers a higher priority task. It gives it the CPU immediately without going to the lower priority task. When it's done, you'll go back to the lower priority task. Okay? Oops. Clear? So this is preemptive. Preemptive, this higher priority task took over the CPU from this lower priority task, and this did not get it back until this is done. Preemptive. Now, what are tasks and what are task states? A task is a simple program that thinks it has the CPU, all of it to itself. Yani a task is a piece of code you write. You can look at it as a simple program that has everything. It has a program counter, has the CPU registers, has memory, have a stack, everything. Okay. So each task has its own stack space to store its own local variables, and it has a priority based on its importance to give it. So the kernel will say, okay, I have 2 tasks. This is high priority. Now you get access to the CPU. No, it's not your turn, and so on. The task code has your application code, the code you wrote to do. A task maybe read the analog to digital converter channel 3, convert the value into temperature, okay, and store it in some place. Another task is something that I go read a value from some place that is a temperature and decide if it's greater than a value I read from another place or through the serial port to run a compressor or turn off a compressor. Okay, so a task would look something like this, and every task has its infinite loop here. This is an infinite loop. So in every task, you may have some data passed in, you may do some initializations, but you will have an infinite loop here to do things over and over again. You have another task 1, task 2, task 3, and so on. So if you are 10 people, you can divide the work among you guys, and everyone writes his own program without worrying how he's going to integrate. You just cut and copy this piece of code and plug it in the bigger program code in the OS. Okay. Each task has 5 states. The first task state is called the dormant state, where the task is resident in the RAM, non-active, and in the RAM where it is only code in your flash memory. You wrote a task, right? And you get code, start task. It's in the microcontroller flash memory program code. A task is created. The code is there, but it's not created. Created means what? Create the stack for it, reserve the stack for it, set its priority, put it in the queue for the kernel to start giving it a turn to access the CPU. Before that, it doesn't have access to the CPU. Nothing will give it the program counter to go fetch its code and execute it. Then, when a task is created, it moves into the ready state. It becomes ready for execution, waiting its turn to execute. Waiting. It's ready, though. And there's a process called context switching that is performed by an interrupt service routine. Periodically checks whose turn to get access to the CPU and decides now it's your turn to move to the running, go start running, and moves it here. Context switching is to switch the context, yani move the stack, move the program counter value, move all CPU register values that are stored somewhere to the actual program counter and point to the stack where the addresses and variables are to start using them. So the switching between a task and another, yani when you move from the ready mode to the running mode, that means there was something running, you moved back to another mode. So changing the CPU program counter, the CPU registers, the stack pointer value, all these, you're changing the context of the CPU, okay? Context switching. And this induces overhead to switch between a task and another. Running. While you're running, there is always an interrupt service routine that I draw here that always periodically checks, oh, it's time. يعني مثلا this interrupt service routine occurs every 1 millisecond. Every 1 interrupt, whoever is running, you're interrupted. Now I go check a queue, for example. Task 1 is running, task 2 is waiting its turn over there, task 3 is there. Task 1 is running. Anybody more important than task 1 came? Or task 3? Okay, task 3, get ready. You're going to become running. Task 1, go back to ready. Switching the context. Controlled by an interrupt service routine, periodic. While a task is running and comes into a state where it is waiting for something to happen, مثلا a delay. Instead of just getting stuck here waiting for 5 seconds, book in the CPU. No, instead of that, you may put in the waiting state and allow somebody else to come access the CPU. After the 5 milliseconds or the 5 seconds expire, you go back to the running mode. So we have the waiting for event state. It is running, but because it's waiting, sit on the side and we'll give the CPU for somebody else, executes. When your event is ready, you come back to running mode. If the event doesn't happen within the amount of time, you go back to the ready mode. Tamam. And a task can be deleted at any time. You can delete a task, meaning you remove it from this cycle. You're back to the dormant mode, where the task is only a piece of code in the CPU. Mashi. So these are the states of a task. either waiting or in the ready state or running, or not created yet, dormant. طيب. Well, you guys are quiet, and it looks like either it's too hard or too easy.
الاثنين سوا دكتور.
الاثنين سوا. Okay. I think for us, when we studied operating systems, we studied the theory of an operating system, how to do scheduling, how this works, okay? The things that you're hearing right now. And the best application we were able to do, go get Linux and start using it for applications and do threads and do whatever, do OS programming. But I feel when we use this operating system now, we're going to look deep inside the kernel. It will give us a perspective and a good understanding, inshallah. طيب. Creating a task. Why do we create a task? We wrote a program. I wrote my program task. Salah wrote his. Talal wrote his. I wrote a code to read the potentiometer. Talal wrote the code to check for a condition somewhere, a flag. If it is up, he goes and does turns on and off LEDs in a certain pattern. Salah does another thing, and so on. Okay. We wrote the tasks. We put it somewhere. We transfer that code into the program memory, into the flash memory. That's the dormant mode. Okay. All the code is there. But how to create it and make it active? Okay. Creating a task is to make the task ready for multitasking, ready to use the CPU, along with other tasks. Okay. This needs from the kernel to what? Decide the starting address of the task, where is the first instruction to be executed in that task. Decide its top of stack. Where is the top of stack of that task? Create a stack for it. So whenever that task time to run, it brings its variables from there. When it's done, it stores its variables there. Its CPU value, its register values, its local variables, and so on. It also needs to give the priority of the task. So when 2 tasks or 3 or 10 tasks are waiting to access the CPU, the kernel decides whose turn it is based on the priority and the arguments that are to be passed to the task. So when you create a task, you usually have a function like this, OS task create. You pass the arguments, a pointer to where the first instruction is at, a pointer to the arguments, a pointer to the stack, and its priority. Okay. Yeah. This is how when you create a task. And when you create a task, block called a task control block should be created. Task control block, TCB, should be created. A data structure, okay, to store the task information, because the task cannot just come like that. A task is a piece of code. You want to start executing it? Executing, add register A with B. What is A and B? A and B, it's only one register, right? They could have been changed by the previous task. So you need to bring their values, their initial values with you. Okay, go get the last the value of I stored in my local memory. Okay, where's your local memory? And I don't know, where is the pointer of your local memory, and so on. Okay, so a task control block is a block, a data structure that is created when the task itself is created and contains the task priority, this task state. I'm in the ready state, I'm the waiting state, I'm in the execution state, and so on, the state, the task top of stack, and other related data. These task control blocks are stored in the RAM, okay, while multitasking is happening. TCBs are usually 45 bytes in the case of this 8086 microprocessor. It can vary, depend. Yani, you need a return address for us, our case, مثلا, for the 16-bit. Okay, that's 2 bytes. You need a top stack pointer. These are another 2 bytes. You need state value, I don't know, 2-3 bytes. You need some مثلا 10 or whatever, maybe any task initially is given some memory space amount of bytes. Every task is given a priority that, so yeah, a few bytes for a task when it's first created. Now, scheduling is the task or is the responsibility of the kernel itself. Scheduling says, hey, it's your turn to use the CPU. You go sit on the side. You're waiting for somebody to come. Okay, he came. You go sit side. Your turn to use the CPU. Okay, higher priority task, a VIP task came. Both of you go sit on the side and you use the CPU. Okay, scheduling. Whose turn it is? What? Okay, and when it's your turn to come use the CPU, you need to go to your task control block, copy your program counter value into the PC counter, PC register, copy your top of stack to the stack pointer register, copy your register values to all registers. Okay, and when you're done, you store them back in the local memory. Okay. Scheduling. So that's the main responsibility of the kernel. Okay, so in scheduling, it is decided when a more important task has to run or not. It occurs, scheduling decisions are taken whenever a task time expires, whenever a task is waiting for an event and it doesn't come within a certain amount of time. It also happens whenever a message or a signal is sent to another task. It also happens when an interrupt service routine happens. Okay, interrupt service routines, the task, the kernel configures periodic interrupt service routines on every amount of time we call ticks. Tick, just like the ticks of a clock. Tick, tick, tick. Okay, ticks. The outcome of scheduling is context switching. Okay, you checked all tasks available, you check their priority, you decide now it's your turn. Okay, switch the context. Yani bring your CPU values, your register values, save them in the actual CPU registers of the CPU, and go save the ones that were there in the task control block of the one that we just took out from the CPU. Generally, in operating systems, when they talk about long-term scheduling, short-term scheduling, long-term, which program should be brought to the ready queue. In short-term, select which one is to get the CPU. It's in the ready queue, but which one? Something more advanced. Not it's out of our scope here. One common scheduling, very famous scheduling algorithm is called round robin, RR. Round robin scheduling. In this case, every task is given a time slice. Okay, you have a queue. Okay, task 1, task 2, task 3. This is the ready queue. Task 1, task 2, task 3, task 4. Okay, I give you 5 milliseconds. Then I stop. Then I give you my 5 milliseconds. You go back to the ready mode. Then I bring this to the execution mode for 5 milliseconds. Then I put it back in ready mode, bring this to execution 5 milliseconds, 5 milliseconds, equals amount of time. Okay. Time quantum, we call it. This amount of time, you call it time quantum. So if you're getting the CPU for 5 milliseconds, 5 milliseconds, 5 milliseconds, this is very, in CPU time, it's long, but in user application, it's really short. You will see as if everything is running in parallel while it's not. Okay, round robin. And this time quantum could be configurable. How much time you're gonna give it. So a queue will look like this. You have a ready list, a linked list. If you're familiar with data structures, we can have a TCB مثلا اللي هو task control block 45 مثلا bytes, another 45 bytes, and a linked list, a pointer that points to the next task, next task, next task. Okay, and you can go pick any one of these to bring to execution. Context switching, sometimes called task switching, is the process of bringing the CPU register values into the actual CPU registers and make them start running. Yani the program counter, task 1 has its own task control block. In its task control block, it has a value for the program counter that points to the first instruction, a value for the stack pointer that it needs when it starts executing, the value for register A, register B, and so on. When it's time, these are brought to the actual program counter. We only have one program counter. When it's time for T2, it has a program counter value that is copied here. So switching, and the value that was here goes back to the task control block of the previous task that moved to the waiting or the ready state. The switching between tasks is called task switching or context switching. طيب. ماشي. Context switching has some latency because you need to push to the stack and pull from the stack. مين طلع؟ أنا أوكي أحمد. Okay. Push to the stack the values of the task control block of the task that just finished or removed or sent to the ready or waiting state, and pulling the values for the task that is coming to start execution. Pushing and pulling the data will imply some latency. Okay, context switching time over here. They call it dispatch latency. Sometimes dispatch latency. Now, when you're multitasking and multiple people are working on something using the same CPU, using the same memory space, using the same file system, using the same parallel ports, these are all resources. And the tasks may need to access this port or this sensor or this memory space. You don't want them to go access them at the same time. One somebody writing in this memory and the other writing a different value, right? They will ruin the whole thing. So there should be some resource management. While I'm using this memory space, you're not allowed to come and write into it. I need to lock it, lock it. When I'm done, I release it, you go use it. To do this, when you want to manage shared resources, you need a way to manage these resources. The most common techniques are mutual exclusions and semaphores. What are semaphores and mutual exclusions? Semaphores is a technique to synchronize activities by making multiple processes accessing a single resource to access that resource one at a time, or control the number of tasks controlling accessing that resource at a certain point of time. So let me give you an example. A mutual exclusion, they call it a mutex, is an object. You can create a mutex, call it mutex, and program object. It's like a key, okay? Create a mutex called global memory مثلا or parallel port mutex, okay? Then when you go to use that parallel port, you check the mutex. It's free, mutex, mutual exclusion. Is it free? It has an ID. Is it free? It will have a state. Free, okay, you take it. While you're holding the mutual exclusion, you locked that resource. Nobody will be able to come. The OS, the operating system, will stop any other task from accessing this resource until you release the mutex, unlock it. Okay, just like the toilet example, and this is copyrighted for this guy. There's one toilet and it has a key. So one person uses the toilet at a time. When you get the key, nobody will be able to use it. When you release the key, you free it up for others. A semaphore is like a mutex, but with multiple keys. Okay, it puts a limit, مثلا 4 keys. So maximum 4 people can use this resource at a certain point of time. So when I request access to a resource, the mutex value is 4, it becomes a 3. I take 1. Then Talal asks for it, the 2 left keys are available. When therefore are using it, nobody can access it further. When I release my key, somebody else can come, and so on. To control how resources. So a mutex is exactly a semaphore with 1 key of value 1. A mutex is a semaphore of value 1. Like, but semaphores or mutual exclusions could cause something called priority inversion. Priority inversion, making a higher priority task wait for a lower priority task to finish. How does that happen? Imagine this case. A lower priority task is running. Okay. This task gets a semaphore or a lock or a key for a resource here. You locked global memory address 1000. You locked it because you want to write on it. So nobody comes and writes on it while you're locking it. A higher priority task arrives that would do that needs the semaphore of the lower priority task. Yeah, you need to access address 1000, but it cannot because it's locked by the lower priority task. So it will have to wait for it until it finishes. So instead of making this finish as soon as possible and going back to the higher priority task, now if a medium priority task arrives, okay, it doesn't need a semaphore. This is working على أقل من مهله, like a turtle. When it's done, so now the higher priority task is waiting and the medium priority task is running. This is making this stay longer. So in practice, this got higher priority than this. When this is done, you go back here, you release the mutual exclusion here, then you go back to the higher priority task here. So priority inversion happened here. The medium priority task got the highest priority. Yani, now we're non-preemptive here. Non-preemptive. We did not allow this to take over or take the key. This is locked. Yani, the only way to make this run is for the lower priority to release the key. So go let it finish. No, while it's running, it's preemptive. We got a medium priority that is higher priority than this one. Okay, so it takes the CPU. So the higher one is waiting for the medium to finish to allow the lower to release the key. So priority inversion. That's a problem.
دكتور هم حلوها بالبروتوكول اسمه لوك فري.
اوكي.
انه بنقدر نعمل اكسس، هو صح في بلوكينج بس ما بنستنى انه اللور بريورتي تعطينا الاكسس للانلوك للكي.
اوكي.
فما في لوك، فاحنا مش مضطرين نستنى اللو بريورتي عشان نعمل اكسكيوشن للهاير بريورتي.
But it has a key.
لا اسمه اصلا هو لوك فري.
lock free.
ما في لوك اصلا.
You don't allow a lock to happen.
Yes.
Okay. يعني okay, that can be a way, but it can hurt though. I don't know about the details, but there's another way to solve the problem. Priority inheritance. So a lower priority task, when a higher priority task is waiting for it, it should inherit its priority. It shouldn't allow a medium priority task to become more important from it. So a lower priority task is running, a higher priority task comes waiting for the lower priority task key to be released. Okay, so it goes back to the lower priority task. Medium priority task comes. Okay, it's not allowed to run until the higher priority task comes, because here, once this is waiting for this task priority is raised to the highest. Okay, so when it's done, this is not higher than it. It's not going to start here. You go, this is higher priority. You go to the, then you're done. You're not cut in the middle. Then you go to the highest. Then you go back to the middle priority task. You inherited the priority of the higher priority task that is waiting for you. طبعا waiting for resources. I have a key for something, and you're waiting for it. And I'm waiting for Salah to release a key so I can release my key, and Salah is waiting for you. We can run into something like this. This car is waiting for this car to open the way. This is waiting for this to open the way, but this cannot open the way because it's waiting for this, and this is waiting for this, and this is waiting for this, and everybody's waiting for everybody. This is called a deadlock. So resource control through semaphores or mutual exclusion could cause deadlocks. So in order for a deadlock to happen, four things have to be allowed. Mutual exclusion condition has to be allowed. Yani I am able to hold the key, and I'm able to hold the key and wait for another person to release another key, hold and wait. And no preemption, nobody is allowed to preempt me if I'm holding a key. And circular waiting. One is waiting for another, one is waiting for two, two is waiting for three, three is waiting for one, and so on. Okay, that's called deadlock. How do they solve deadlocks? There are different ways, three ways. The first way, to prevent it from happening. Prevent, don't allow deadlocks to happen. By not allowing one of the four conditions here. So don't allow mutual exclusion from the beginning. Or if you have a mutual exclusion, you cannot be holding it and waiting for something else. And you prevent any of these conditions to happen, then you prevented deadlocks. That's a way to avoid deadlocks. Another way is avoidance. By planning. Plan. You have a semaphore. If I give the key for this resource, is there a probability that anybody is going to come ask for the same resource while holding a resource B? It's a big, there are algorithms here. So you classify the tasks into, it's safe to give a resource to lock, it's not safe, and so on, states. There are algorithms here. You avoid a deadlock to happen. You allow the conditions, but you try not to give, in some cases, mutual exclusions to some resources if this may cause a deadlock, using some algorithm. The third way is detection. Don't do anything. Allow all conditions to happen. Don't plan for anything. But whenever a deadlock happens, just restart. And this is what most of operating systems do. Most of operating systems like Unix, this is what they do. They allow, if any time a deadlock happens, just restart. لما الجهاز يعلق يقول لك you got that blue screen or whatever. Most likely something like this happened. Resource allocation and planning, many algorithms, and I don't want to go over graph algorithm, bankers algorithm. Okay. Inter-process communication. قديش صرنا بنحكي؟ Okay. Yalla, almost done. There is a direct communication between processes. You can make a task 1 directly communicate with task 2 by establishing communication links. Okay. These links can be unidirectional or bidirectional. We call them pipelines. You can open a pipeline between a task A and task D, A and B, and start sending tasks directly between them. There are indirect communication. You have a mailbox, you go put your message in a mailbox, and task 2 will go read that message from the mailbox. Mailboxes can be blocking or non-blocking. بمعنى, I go read a mailbox. If I find the message, I bring it and go back executing my tasks. If I don't find a message in the mailbox, I also can go back. This is called non-blocking. And you go check anything new. I have a message. Yes, no, whatever. If it's there, I take it. If it's not there, I don't take it, and I go back to my program. Blocking, no. In blocking, you go check for a message and you keep waiting for it to come. If it's not there, you keep waiting. You're stuck waiting for a message to arrive. That's called the mailbox blocking. Mailboxes for synchronous. And there's a client-server communication methods using RPCs, remote procedure calls, sockets, whatever. Not our scope here. In micro-COS2, the ways we have to communicate using global variables. When you use global variables, you need to use mutual exclusion. So if you have integer I in the global memory, task 1 uses it. Okay, if it's adding something to it, in the middle, another task comes and interrupts the lower priority task, and wants to manipulate or change the value of the same global variable I, you shouldn't allow that because you're in the middle of something there. Okay, you need to lock it. If interrupt service routines involved, need to disable interrupts. If you're accessing global variables. Or you need to check the local variable periodically to check if it has changed or not. Another way, other than global variables, creating something called mailbox. Mailbox is one box. You write something in it. Somebody else can come and read it. Task 1 can write in it. Task 2 can write in it. But because it's a mailbox, it has a nature, and you can write or read. Nobody can interrupt you while you're in the middle of writing a message, okay? Like a global variable, I, مثلا. And multiple mailboxes can create a queue, message queue. Okay. Okay, so you have a mailbox, you can post to it. Task can either accept, يعني هذا code. When you write code, you can go to say task accept from mailbox 1. Accept is non-blocking, or pending blocking, and you will stay waiting, keep waiting for a message to be written here. When it's written, you go back. If you say pend, if you say accept, if there is something there, you get it. If it's not, you go back without reading it. Message queues, FIFO. Okay, I'm going to move faster. Memory management. In micro-COS2, there is no problem because every task has fixed memory block for the task control blocks, the TCBs. Okay, they're not variable, so there is no memory allocate and free. That will cause some fragments of memory that may be scattered here and there. So you need to do defragmentation every while to put things together. This problem is not in OS2, micro-COS2, because we're using fixed size memory blocks. طيب, we're talking about micro-COS2. Micro-COS2 is by a company called Micrium. And today it looks like either they changed their name. I was checking it before the class, or somebody bought it from them. Anyways, I'll go with it with you. They have several products. So Micro COS2 is free. You can get it for academic research and educational purposes. But they have other products that you can buy. And in the past, I remember I bought Micro CO CAN and Micro C Probe. What is it? Yeah, Micro C Probe. That have any pre-programmed plugins that you can put in the OS2, and Probe is to create visual graphical interfaces to read from there, display things on your screen, and so on. CAN has libraries to configure the CAN bus. Honestly, I got it, but I paid for, I think I lost the money. I ended up doing my own libraries at the end. I didn't try others, but GUI, USB, file system, whatever. Okay, let's see a demo. Let me show you Micrium first. We're almost done now, and it's not going to be boring anymore. I didn't share these slides. I'll share them after the class. Well, depends if you want. طيب, so if you go Google Micrium, okay, this is what you're gonna find. In the past, I used to find Micrium.com. Okay, it was a company, a standalone, and it has been a while since I last checked it. Okay, and how the OS was developed has a nice story, by the way. Anyways, Google Micrium. Okay, the first link you get is this website, Silicon Labs. I don't know if it's the same people or somebody else, but Silicon Labs. Micrium OS, software documentation, Micrium OS, real-time OS, and stacks. Full feature embedded operators, including networking, communication, and file system, ported to over 50 architectures. The good thing of this thing, OS, guys, when I downloaded it the first time, long time ago, it was there for the HCS12. You were able to find for PIC controllers, DS PICs, other controllers. You can write code that is hardware independent, because the OS will serve as the interface between you as an embedded software developer and the creating the task is going to stay the same. A lot of services code is going to be the same, and the OS will behave as the interface between you and the hardware. Like full feature embedded software operating system with automated project generation ready for devices running on Silicon Labs platform. Software, real-time kernel talks about it. See, there is a real-time OS 3 now version. I didn't check it. It has support for TCP/IP communication, USB devices, USB, CAN, Modbus, storage file system, and these are the architectures that supports Toshiba, Texas Instruments, Cypress, Atmel, ARM, and here's the download center. And honestly, when I downloaded it, I'll share it. You must be registered user and log in. Okay, you guys, you can register and log in. I know it's free for our HCS12. I'll share it as well. NXVC, here are the, and they have examples. Microchip is Microchip, DS PICs, whatever. Different architectures, PIC 32, PIC 24. Oops. NXP is in the past. NXP is old Freescale. So I imagine you'll find the HCS12 here. Okay, power architecture S32K. Actually. So here, you can find sources, you can find documentation, a lot of things. For you guys, I'll upload it to e-learning. And here it is. Here it is. Here's my C. I'll share the. I put it on my C root because there are long, paths, directory paths. So when it gets long, if I put it on my desktop or something in the compilation, I get some errors. So it's here, Mycrium. I'll give you something like this when we're done with the demo. Mycrium. When you go into here, you go to software. Ignore all these. Go to evaluation boards. Freescale. DG256B. Dragon12. And originally this was until you get to OS probe LCD. Okay, this is the path you follow, and this is the project. You open it, OS probe LCD. When I first got this, it was made for a board having an HCS12 microcontroller that is different than this mini Dragon board. Anyways, I had to do some modifications in the core of the kernel to make it work, and it works now, so you don't need to worry about it. And this is by Jane. Yeah, Jane has a book about the story how he made this OS. He talks about how he was developing some software using an existing OS. He felt frustrated. The things were very complex, and then he decided to do his own OS, and he did this OS. See, here are all the data source files, all the source files. Now, as I told you, it was meant for a, see, any sources, OS core, flags, mailboxes, memory, mutual exclusion, semaphores. And I'm not going to go over all these things today because it's going to take forever. Okay, the hardware, serial monitor, whatever. I'm going to just show you how you can use it and configure, create new tasks. Okay, you can play with everything else later on. But as I told you, when this was done for the hardware that I used in the at that time, the board used to have keypad, used to have multiple 7-segment displays, used to have a LCD and many things. Okay, so we're not going to be using these. Okay, we start with the application app.c. app.c and the app configuration.h files. These are the two files we're going to use, okay? And I meant to have old files, old tasks here so we can mimic what we can do. So this task in the demo you download already has 4 tasks. A task that starts all other tasks. Okay, or 2. Start task and task create. This does the initialization. This creates all other tasks. An LCD task to write something on the LCD. 7-segment task and a keypad task. And I think I wrote this swing task a long time ago. Yeah, I have a comment here. Today, let's do 2 tasks here in our class. Let's do 2 tasks. In parallel. We write them in a way that they look completely independent. I don't, when I'm writing task 1, as if I'm doing an independent program unrelated to any other program. So when we create a task, first we need here are the variables to define the OS stack. OS stack. This is the one. If you right click and go to see what is OS stack, OS stack is a data type, and you can look deeper into everything here. You have the source code. Every task should have a stack, should have a prototype. This is the main task, the initialization of the OS. We don't touch it. And this is the start task that creates all other tasks. Don't touch it. And here are the tasks that are to be created. These are the tasks that we had in the demo we downloaded. I'm going to comment them out now in a second, because so here you create the first task, here you create the second task, Here you create the third task and you pass all the variables. Where is the stack? What is the priority? What is stack size? And so on. Names, errors, and so on. Then you come to the task code. Here's the code for the first task. It has its infinite loop. Then this is a task. This is another task. Start here. It has its infinite loop. Then you have another task and so on. That's it. And the configuration file here, you define the task priorities. What is the priority? Lower number means higher priority. So the highest priority is the number 1. Second highest is 2, and so on. Okay, and the stack size, you define it here. Every task has a stack size. How much stack size you want to give it in bytes. Any other stuff you don't need to worry about. I think where I did the clock, if you go run it on a different hardware or a different clock, OS configuration maybe. I think here there is some configuration I did. And you need to the deep understanding maximum events of how to مثلا configure the PLL clock. This is meant for 48 megahertz PLL, okay? Based on an 8 megahertz oscillator. If you go run it on a different hardware, you need to go change those values. I think I had them. Is it in the configuration? No. OS configuration. See, we're playing with the source code here. You need to be careful. The core. It's somewhere. I'm not going to waste time looking for it, but it's somewhere here and a while ago that I changed. So let's make 2 tasks run on this controller, on this HCS12. Let's download the OS here and have 2 tasks. مثلا one task doing turning on red, green, blue LEDs on the RGB. The purpose is to do multitasking, not the task itself. RGB مثلا with 500 milliseconds delay between red, green, blue forever. And maybe another task to blink the 7-segment display on, off, independently of those other red, green, blue. You can do another third task to go change the value of I that will be displayed on the 7-segment, whatever. So this is how we start. Let's create something called class demo task 1, class demo task 2. So to start, the easiest way is to start by copying. Oh, by the way, here there are data types. So any data type here, CPU underscore integer 08 is the size, and U is unsigned or signed. When you want to go define a data type, you can say OS like here, integer 8-bit unsigned. This is similar exactly to unsigned character. If I want unsigned integer, I can say CPU integer 16 U unsigned. If I want signed, I say signed, S signed. This is handy and useful when you move to different hardware platforms, because the CPU here has this data type defined here as a data unsigned character. Okay, and assigned is assigned character. 16 unsigned integer. Okay, long 32, and so on, floating. So when you go to move to other hardware, you don't. If they have different data types, the OS will eliminate this issue. One more thing, there is a function called OS time delay HMSM. HM hours, minutes, seconds, milliseconds, where you give it the value of the hours, minutes, seconds, milliseconds. And every task has to, this is an interrupt-based delay, ماشي, based on the ticks from the kernel. And you need to go deeper and figure that out, the ticks, the kernel, how it does work. Anyways, not our business now. Every task has to create, to include a delay. حتى لو 1 millisecond. Why? To cause an interrupt, to release the CPU, to give the kernel time to go check other tasks and figure priorities and give turns on the CPU. Okay, so this is a rule of thumb that we need to keep in mind when we write our tasks. Right, let's go do this. And I'm gonna remove this task. I'm gonna create 2 tasks now. Copy. I1, add the 2. Oops. First one, let's go call it class demo. Class demo 1. T1. Class demo task 1. ماشي. And the other one, call it class demo task 2. And this would need a stack size. Let's use the same analogy. So we class demo T1 T2 size. We'll go configure that later. ماشي. طيب, then we need to do the prototypes. Same thing, task 1. Let me copy this. And task 2. Okay. Then start task, application start task. We don't touch these. These are the old tasks we had. I can go comment them out. I don't create them, مثلا, comment. ماشي. Here. And let's create our task. Let's go get that keypad task, this one, and do something similar. Control C and Control V here. Just let me copy the text we did here. That's demo T1. T1 stack. We'll fix all these things. Priority, we didn't set it yet, but we will. Okay, and I'll copy this. I'll copy this and create task 2. So just replace T1 with T2, task 2, task 2, 2. Task 2. طيب, we created the tasks now, then we need to write the task. Okay, this is its name. Class demo T2, T1. Class demo T1, T2, مش مشكلة. Okay, these are commented out. يعني these are not going to be created. Okay, I can delete them. I can comment them out, but it doesn't, no problem. They're only going to take some flash memory space.
حياكم الله دكتور.
ثابتكم الله. طيب, let me go copy this task and make something similar. هذا الكيباد. We did the keypad. Let me copy this. Control C. Let me delete this. I don't know what this is. But يعني okay, one. Let me do this one. Class demo task 1. Class demo task 1. مثلا I don't know. Okay, task demo, class demo, task 1, same names. كلياته I can remove. Keep this while loop, infinite loop. Here, I also can remove all this. This is task 1. Well, I don't think we need this. And this is task 2. Then you change T1 with T2. The periodically blinks 7 segment display. طيب, and call it T2. طيب, this one, you can, this is always true. While define true, or while 1, you can write while 1 for whatever. And this is the delay. طيب, what do we want to do here? We want to do the red, green, blue LEDs. Red, green, blue LEDs are port, what were they? Do I still have, where is the data sheet? Yeah, here. Red, green, blue LEDs are port, anybody remembers what are the ports? Here, port, hey, port P4, 5, and 6, right? 4, 5, and 6. So to turn them 4 on, I need to write a 40, صح? 4, 0, 0, 0, 10, 1, 0, 0, 0, 0. 20 will turn on 20 hex, the other one, and then 40 will turn on the third one. Yeah, like port P. So here we need to define DDRP as output, right? port P output. Then here, what do I want to do? I want to say port P equals 0x10, right? Red LED on. Then some delay. How much delay? 500 milliseconds مثلا. 500 milliseconds. نص ثانية, huh? Then what is this? Right. Then port. Let me copy. Then the red, then the green. Then 40 for the red, the blue LED. Forever, خلاص, huh? Infinite loop. You want to read A to D, you can read A to D. You want to do whatever you want. It's a full task. ماشي? Done. طيب, for task 2, what do we want to do here? Port H, we want to blink it forever. So DDRH equals 0x FF. Port H output. Then while ever forever, we initialize port H. مثلا PTH equals 0x00. Then here port H equals tilde or not, or in one's complement of port H. And delay, how do you want to this slower مثلا 1 second. 1 second بتكون here. Hours, minutes, seconds. Seconds. This is 1 second. 500 milliseconds. Oh, I have to do 500 seconds. 500 will be here. Sorry, guys. 500 milliseconds is the last one. 500 milliseconds. So we'll be having red, green, blue doing every half millisecond, and every 1 second, and 1 second on, 1 second off for port H. So done. We can add as much. This is forever. We want to add another third task, fourth task. In micro COS2, we can do 255 tasks. Right. Then we go to configuration.h, app configuration.h. Here we need to give the priority. We need to give the priority, so we can do the keypad. Let's copy the keypad because we did before. So here is class demo T1 task priority. What is the priority we wanted here? مثلا 11. We can keep it 6. مش مشكلة. 6. And task 2 will be same priority or less priority, 7. Task 2. And let's give them some stack space, 256 minimum. As demo T1 256. Oops. And T2 up. And T2 some stack space. And we are done. We are done here. Let's compile. Takes time. No errors. I can turn on my my microcontroller, serial monitor, run. Okay. Well, COM3. Okay. Programming. All done. Turn to close this. Reset. Let me stop sharing. Where's my other camera? Done, 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 done. Here's my other camera. Let me spotlight it. You see it, huh?
Yes, Doctor.
Here's the 7-segment display. Blinking. 1, 2. See, every 1 second. While this is the red, green, blue. Red, green, blue. Red, half second, huh? Both running in parallel, written by 2 different people, yani pretending, without having to coordinate or do anything. You can do whatever else you want. See, the 7-segment is blinking. The red, green, blue is also turning on every half a millisecond. I think you're able to continue from here. I'll stop if you don't have any questions. I'll stop and you can stay for questions. Thank you very much.